to my lecture today. I believe everyone is hearing me clearly. Uh, Thank you so much. Thank you for confirming that. Today, basically gonna walk everyone through what I call machine learning with K-nearest neighbor algorithm. The other time, I actually introduced the class to Introduction to Machine Learning. And from there, in our last lecture, I actually walk everyone through what I call the supervised learning. Uh, Under that supervised learning, I actually treated what I call the decision trees algorithm. But today, we actually are going to be discussing on another form of algorithm using supervised learning that I'll call the K-nearest neighbor algorithm. Okay, so let's get started. Uh, Let me just say that the KNN algorithm is actually a non-parametric way to classify items into different groups. Of course, I told you the other time that uh, we actually use supervised learning to do classification. We also use supervised learning to do prediction. So today we actually gonna discuss the KNN, which is one of the supervised learning, how it can be used as classifier. Okay, and you know what? The KNN is very, very simple to use, and I'm actually gonna say it's a non-parametric. You know, those of you in statistics actually know what I mean by the non-parametric. It means it doesn't require the stringent assumptions of normality. Okay, so the task today, you know, just like the example I cited the other time in my last lecture on decision trees, we actually have a classification problem. I think I gave an example on credit card application. You know, some applicants actually apply for credit card, and of course, you know, before they could be considered for that, the company actually got some information which has to do with the gender, the credit history, as whether they got job or not, whether they own their house or not, you know, among other questions. And because the fact that the credit company actually have historical data. Okay, so if they really want to classify the new set of applicant, of course, they can actually use past information to do that. So the KNN can actually be used, you know, can be trained on the past data, you know, to be able to figure how, you know, how they can actually use that on the test data, like a new data, to make what I call an educated guess, okay, on where to actually classify the applicants. Okay, the applicant is either to be approved or for credit card or not. Okay, so the KNN is one of the supervised machine learning, and of course, you know, the supervised machine learning is when the data set you have for every input you have an output, well, which means we got label. Okay, so let us see how the KNN actually works. I want to tell you this: we live in a world where we cannot be in the same class. There's a variation in this world, and because of that, we basically going to be faced with classification issue. Now, when you take a look at what I have here, we got green and we got red, and if you take a look at this guy here, uh, we're actually looking for where to classify that, whether it's going to be classified as red or it's going to be classified as green. And if you take a look at the position that is occupying on this four cardinal point, uh, we have other balls of other colors that may also be occupying the position. But let me tell you this, the idea behind the KNN neighbor is just like, okay, let us use the idea of the similarity, let's compare the distance, and, you know, the distance to others is basically going to be used. The knowledge of the distance to others is basically going to be used when we are trying to classify. Okay, so that is exactly what we want to do here. Okay, so the idea, something that we call similarity index. Okay, so which means what we basically going to do is we actually going to use an algorithm by finding the distance between the mathematical values of the point. Okay, so which I'm still going to show you how that is going to play out. Okay, the assumption for KNN, like I said, is non-parametric in nature, so it doesn't require the stringent assumptions of normality. Okay, so we are fine. Okay, so we are fine using it. Okay, so generally, I want to revise with you the idea behind the supervised and unsupervised learning. I just want to actually, you know, revise that with you again, like having a recap so that you'll be able to connect, you'll be able to follow up with what we're actually, what I'm explaining now. So this is a supervised learning because the inputs X1 and X2 and there exists the outputs, okay, the response variable, the one, some people can also call dependent variable. So there exists a class here, it's more or less that you are actually act as a teacher supervising a student where you say, okay, my student, if something is, if a variable is 10 and another variable is 100, then we can actually class that as squared. Okay, you are giving the answer to the student, and that is why it calls supervised learning. Okay, now and it's okay, when you have another one, that is, if a variable is 2 and S2 is 4, then you actually going to classify that as rows. Okay, so this is a supervised learning. The data set that here is actually required using a supervised learning approach because the dependent variable actually exists. But when you take a look at this, we only have inputs, but there's nothing like a class. Okay, so this is an unsupervised learning. We actually have a way to figure this out. We have some algorithm too that can be used under unsupervised learning that I'm actually going to discuss in another lecture. Okay, so using the KNN, it's we're actually going to compute, the distance will be involved. Okay, the neighbor. When I say neighbor, when I'm living in the street, okay, so if you compare our street with another street, okay, so those of us in our street are neighbors. In a way, we are similar, similarity due to in terms of where we live. Okay, the fact that we live in the same street, right? So and of course those that live far away, I know the distance actually exists between us. You understand what I mean? Okay, so the distance measure we actually play a key role in KNN neighbor. So distance are used to measure what I call similarity. Of course, that really makes sense. Because the similarity that we're talking about, uh, among items that are kind of similar in terms of maybe probably position or whatever they occupy, we don't expect the distance between them to be huge. And I also want to remind us, we have different kinds of mathematical way to figure out distance. There's one that we call a Maranobie distance, Euclidean distance, Army distance, and Minkowski distance. Okay, so which means we basically gonna make use of distance, calculate distance, okay, as far as the KNN is concerned. Okay, so I made mention of calculating distance, and of course, the mathematics behind the KNN is actually getting the distance between any 2 points. Okay, so if you're talking about between set of P and Q, where we got a P1, uh, P2 up to Pn, and we got a Q1 up to Qn as well. So the distance can actually be computed using what I have here. Okay, so this is a short form of what I have here. Okay, so because a distance is involved, we need to really understand the property of distance, right? Okay, when you take a look at the first one here, the distance between x and y can be equal to 0 or can be greater than 0. Of course, if the distance between x and y equal to 0, so it means they are more or less occupying the same position. If the distance is greater than 0, of course, it means they are, apart. You get what I mean? And a situation where the distance between x and y is the same as between y and s, then we call that symmetric. Of course, you remember a matrix, mathematics, where if I have a matrix and if the transpose of a original matrix equal to the matrix itself, I believe we used to talk about symmetric. And of course, you remember the normal distribution, where when you have a center 0. So when you divide that a normal curve into 2, looking at the center, you're basically going to see that the distance from the left to the center is actually going to be the distance from the right to the center. Okay, and that's why we said that a normal distribution is symmetric in nature. Okay, so the talk cannot shorten distance. When you take a look at what I have here, the distance xz, okay, it's actually, if I'm talking about the distance here, okay, it's going to be less or equal to the distance between this guy plus the distance between that guy. So we just wanted to take note of this. Um, Behind any machine learning approach, there exists a mathematical theory. Okay, and we need to be able to review that for us to be able to understand how machine learning work. Okay, so we have another distance measure that we call a Minkowski distance. Okay, don't forget, if you basically want to figure out, what does it mean for something to be similar? Because for something to be similar, it means they can actually be grouped. They can be in the same class. Okay, if they're not similar, then it should go to the other class. And that is why the distance measure actually going to play a key role okay, in investigating this. So I'm going to say we got different kind of distance. We have a chef distance. We have a Mahalanobis distance. I remember the Mahalanobis distance is actually used in a classification, in discriminant analysis. Okay, so in discriminant analysis, of course, we make use of a Mahalanobis distance. So as far as the KNN is concerned, you need to be able to know the types of distance or you're actually going to use, okay, between the Minkowski or Shepshire, Mahalanobis, and the like. Okay, so going into the KNN now, let me just for us address some measures, nearest neighbor and exemplar. Well, some of us, we really know about arithmetic mean, we know about geometric mean, medoid and centroid, but you know what? I'm basically going to spend some time talking about arithmetic mean and the geometric mean. When you take a look at the arithmetic mean, geometric mean, all these also play a role in a KNN. Okay, you're going to see how this play a role. If I have observation 2 and 4, if I find the arithmetic mean, of course, the arithmetic mean is actually going to be the center of the two numbers, right? So which means 3 is actually going to be at the center of 2 and 4. That is exactly what it means. So, and here we are actually telling the world that, okay, since 3 is at the center of 2 and 4, then it should represent them. It should represent them provided, the variance, the standard deviation is very, very small, because before you can actually rely on mean to represent, before you can rely on a particular data point to represent the rest, you got to make sure that you measure how far apart that particular data point is away from the rest of the observation. Now, when I go to 4 or to 3 observation now, accidentally, I got 4, which is part of the original. Here, 3 that we got is not part of the original data. So here, this is part of the original, so which basically means 4 can actually represent 2 and 6. Now, what of in a situation where I have 2, 8, 11, you can see on a number plane. Okay, 2 here is far away from 8 and 11. If you want to base it on the neighbor now, okay, you actually expect 8 and 11 to be neighbors. You get what I mean? And 2 is far away from them. And of course, what is going to be at the center of that is actually 7, which is basically going to be the mean. And, that could serve as a threshold, to classify numbers here. If you want to classify the set of numbers here into 2 categories, you get what I mean? Okay, so with a situation where I got a repeated observation, like 2 repeated 3 times, the guy is and you got 11 and you're trying to find the mean here is actually 5. So which means for the data point, of course, if the center is actually indicated. Okay, so and we are talking about geometric mean. Okay, the time between any 2 geometric sequence is actually the geometric mean. How do we know that? Okay, if I have 4, 20, 100, if you look at this, you're going to see that if I multiply 4 by 5, I got 20. If I multiply 20 by 5, I'm actually going to get 100, so, which means this is more or less like a factor of 5. Okay, so how do we get this 20? Let's say for instance, I only want to focus on 4, 20, and 100. Now I'm going to tell you that the 20 here is actually going to be the geometric mean between 4 and 100. And don't forget, if I actually want to get, the geometric mean, since I have to observation is basically going to be 4 multiply by 100. Okay, because you got two numbers. Okay, the actually, which is more, which is the same thing as the square root of 400, which is going to be 20. Okay, and that was why the 20 here is actually the geometric mean between 4 and 100. And what we actually, the takeaway from here now is that the geometric mean, okay, what you have in between geometric sequence is actually geometric mean. Okay, that is what that is a takeaway, okay, from that. Okay, so is that is a takeaway now? Okay, I'm actually gonna go into something else. Let's now focus on the um, the nearest neighbor search now. Okay, we have some set of observations, and we basically want to classify them using what I call the nearest neighbor search. Now let's get started. When you are given a set P, okay, an uppercase P, I want you to take note of that, right? Of endpoints, okay, this very P, okay, there's so many points on that particular P, endpoint actually mean maybe you have a P1, P2 up to Pn. Okay, in a real number, I know you have it in real number and in D-dimensional. Okay, you have it in real number, you got some features, right? And the other time, the example I was actually giving everyone, we actually want to classify, applicants for a credit card into whether they're going to be approved or not. The variables that we're actually going to put into consideration, what I mean by features, what I mean by predators, what I mean like independent variables. Okay, that is exactly what we're trying to say. That is what that D represent. We have that in D because we actually, the bank or the credit card company is actually going to base their decision on those variables like the credit history, um, like the whether they have job or they own their house and stuff like that. So we have this as point now, and we actually want to find the data structure we have, is that giving a query point Q. Okay, this is a query point, right? This particular query point it's more or less like a new applicant that apply for the credit card. What we're actually going to do now, we want to find the nearest neighbor of P of Q in that P. Okay, that's exactly what we want to find out. Okay, so what we're going to do now, if we have it like that, and we actually want to use the KNN, okay, we actually we need to do it in a way to reduce complexity, okay, and we need to have what I call a threshold on the majority, okay, and having a threshold of the majority, okay, uh, that will enable us to be able to figure out what is the number of neighbors, because if you want to start with, you basically need to figure out what numbers of neighbors are you actually you want to start with. I can decide to say, okay, the K here actually represents the numbers of neighbors. Okay, so we can vary that. Okay, so if you choose K equal to 5, okay, K equal to 5, it means I'm actually choosing 1, 2, 3, 4, 5. And some of you may be wondering the other time, uh, that why am I calculating the mean? Why am I calculating the arithmetic mean, the geometric mean? If you take a look at this particular point now, okay, we're actually trying to say the nearest neighbor to this point are this one, are this, and that. Okay, I wanted to take a look at that. And don't forget, we got two different stuff. Like you can see circle, you can see something like X, right? Okay, I want you to take note of that. Okay, So we need to decide if majority of instances over a given value of k here, and we are actually suggesting k to be equal to 5. Okay. Now I'm going to give us a very practical example. Okay, and probably this example is basically going to be on 4 point, and maybe give me this 4 point. Don't forget, here we got two features, right? Two independent variable. The first one represents acidic durability. The second one represents strength. Okay. When the acidic durability is 7 and the strength is 7 of probably of a particular item, okay, that was classified to be bad. This is from the data that we have, the historical data that we have. This is a supervised learning because the outcome variable is the label. This data actually have a label, okay, which is this guy here, okay, and that was why we actually going to use a supervised algorithm, and one of the supervised algorithm we want to use is KNN. Okay, we have the first one, the second one. When it's 7 and 4, it's classified bad. When it is 3 and 4, it is classified good. When it is 1 and 4, it is classified good. For now, there's no any issue. For every input here, we have an output. And you know what? What is the problem? Okay, the problem is if we have a new data point, maybe probably we know the acid durability and we know the strength, and we basically we're going to be faced with a problem of classifying that into being bad or being good. Okay, so which is this guy here, point 5. Maybe we have a new entrance now. We have a new data point now. The acid durability is 3, the strength is 7, and the question now is, how can we classify this? And this is a classification problem. So how do we go about this using KNN? So what I'm going to show you everyone now, I'm going to show you the mathematical way, the manual way to figure out, to use KNN for classification. But I can tell you, when you have large data set, okay, we can actually use Python or R or whatever statistical software, to figure that out. Okay, but I'm going to show you the mathematics behind, the supervised machine learning algorithm in the name of KNN. Okay, so, what we're trying to do, one of us have a scatter plot of that, okay, of the strength against acidic durability. Okay, we actually have a diagrammatical plotting of this guy against this guy. Okay, and we plotted all of this, okay, including the one that we don't know the label. Okay, so, and that was why you actually see this guy here. Okay, this particular point, where can it be classified? We already know, this is a 3 and 7 that we talk about here, right? Okay, so we already know where all these are classified. Okay, we know where this guy, where they are classified. As you can see, some are bad, bad, good, good, but we don't know where the 3 and 7, this guy here, will be classified. And what we actually want to use now is to use a KNN algorithm. Okay, so I'm going to show you how the KNN work. We basically need to figure out the distance, particularly the Euclidean distance will be used. The other time, I show you different kinds of distance that you can find. There's shape distance, there's a Malanobit distance. The Malanobit distance is actually, that is used often in discriminant analysis. Okay, so here what we basically are going to do, this is our data point, right? Okay, the P1 up to P4, but this 3 and 7 here is the one that we basically, seeking to classify. You get what I mean? So what we basically gonna do now is to find the distance. We basically, if you take a look at the formula that I'm actually using here, for example, if I want to, I'm going to find a distance, between this guy Okay, the x1, I'm going to call this one the first coordinate here is going to be x1, and I'm going to call this guy s2. This is a y1, this is a y2. That is exactly, and I'm actually going to find the square root. The formula that I'm actually using now, okay, is just x1 minus x2, okay, or squared. Okay, so so plus, okay, y1, okay, minus y2 or squared. Some of you who did addition and math, I know you've seen something like this before when you are trying to look at the distance between 2 points. Okay, so very, very useful in KNN algorithm. Okay, so you're gonna do that here. That actually give 4. You also do this one and that too. So all of that is you're gonna find the distance between each of that and that particular point, coordinates that we actually want to that we're seeking the classification for. Okay, so when you do that using this formula in each case, you're basically gonna have this result. Okay, so that is what you're actually gonna have. Okay, so that is what you're gonna have. Okay, so the next thing you basically are gonna do when you have that, okay, initially, you actually from your data, the case 1 is bad, bad, good, good, as it was given in the data. You can see that, right? Only that we're seeking to, you know, to figure out what the classification for the P5, point P5 is basically going to be. Okay, so we actually need to decide on the nearest neighbor. Okay, we can decide to use the 3 nearest neighbor. I got 4 data point. Okay, so you can decide to say, okay, you need to decide on the number, on the values of the neighbors. Okay, because when you have 4 point, okay, the maximum neighbors that you can actually have is going to be 3. Okay, if you say 4, then that is not going to be fantastic. Okay, I'm going to say that again. You have 4 data point, the maximum neighbor is basically going to be 3. Okay, now if I want to base neighbor on the 3, I'm going to look at those 3 numbers that are very, very close. Okay, this is the 3, 3.6, and 4, right? Okay, using the 3 neighbor, right? Okay, so I wanted to take note of that. So that was why we actually put this color here. I put this color here. I put this color here because they are neighbors in terms of, if you want to talking about neighbor, you actually look at the distance. Okay, 5 is far away from them, and the approach I'm using is a 3 nearest neighbor approach. That's what I'm using, right? Okay, so now if that is the case, using that now, I will be able to predict for this guy here. Okay, if I want to predict for this guy whether it's going to be good or bad, okay, I'm going to look at out of the 3 neighbor. Okay, I'm going to base it on probability. How many of these 3 neighbors are good and how many is bad? I'm talking about the 3 nearest neighbor. Okay, and when you take a look at this guy now, okay, good is 2 out of 3, right? Okay, and we live in a world where there's a variation, and we normally focus more on the frequency of occurrence. Okay, good or occur more, more than the number of times the bad occur in the neighborhood arrangements. Okay, and because of that, because we got 2 good and 1, of course 2 is greater than 1, then that the data point is basically going to be classified as good. Okay, so don't forget we're using the majority rule, right? Okay, and that was why I'm actually going to call that point to be good. So which means that is going to be classified as good. Okay, so we classify this as good. Don't forget the we use three neighbor, we use three nearest neighbor. Okay, we use three nearest neighbor. Okay, and of course the number of good is actually more than the numbers of bad. You can see the reason why I said when you have four data point, you cannot use your nearest neighbor can be four. Like in this case now, where it is four, so which one are you going to choose? Because if it is four, you're going to choose all of them, which means bad, the probability of bad and the probability of good will be the same. Okay, so that's why you have to choose your the number less than the totality of the data point. Okay, so this is where I'm actually gonna stop today. This is just an introductory, it's an introduction to KNN, as we're still going to do more on KNN. But this is just to introduce you to the mathematics behind KNN algorithm. But you know what we're going to do next time? I'm actually going to walk the class through how you can implement, the decision tree and KNN using R software and Python. That's what I'm going to do next time. Okay, so this is where I'm going to stop today. Make sure you all stay safe and have a lovely day. So bye for now, everyone.